based in Auckland, Wellington, and Singapore. I'm also the founder of Stray Rats Custom Motorcycles, and I'll talk about why this is relevant a little bit later. So I had a goal with this project, well, a couple of goals really. I wanted to combine two things that I really love doing into one package, and well, in this case that was building and riding motorcycles and going and trashing people's networks. Creating a Wi-Fi review platform in the process would really be a bonus for the day-to-day type stuff. So some real high-level requirements, it had to allow for a wide range of software to be run. I really didn't want to be locked down to a specific tool chain or anything like that. Had to be able to operate for an extended period of time, so I mean 15 minutes worth of Wi-Fi testing here is really that helpful. Had to cater to a wide range of attacks, and still having VM left over would be a real bonus. But let's talk about wardriving for a little bit. So I'm sure you're all familiar with this, but for those of you that aren't, basically wardriving is the process of mapping wireless networks by somebody in a moving vehicle. So essentially what happens is you sit in a vehicle with a laptop and maybe a USB Wi-Fi interface or something like that. You drive around, collect information on said access points, and map said access points and then profit, maybe? I don't know. The subtlety, or rather the lack of subtlety with this was something that kind of bothered me. It's sort of easy to spot, right? And you can't exactly park your SUV on the footpath in the middle of the CBD. That and the whole tinted windows and aerials on the roof thing was never really my style. So if you'll excuse me, I think I may have come up with a solution to this problem. So let's talk about the why, Wi-Fi and Rust. This is where Stray Rats Customs were involved with the build. Initially, the idea was to use a old 70s cafe racer, but it turns out blowing crank seals is never really a good way to get down from Wellington in one piece. So this is a Yamaha TRX 850. It's a parallel twin 850cc motorcycle. It's at about 9 horsepower, and they built it with a gimpy crank, so it makes it centrifugated. What we did is we fabricated some stainless steel mounting brackets that live throughout the bike and the saddlebag so everything keeps shape. There was a valve train removal that had it. Thankfully, Yamaha kind of sorted out the valve train pretty well, so all that required was setting valve clearances and doing a little bit of regrind. Carbs were rebuilt. There's a full exhaust system on this, so for the first 2 rows, if you don't like carbon monoxide, tough shit. A performance trim was done to make sure everything runs well. There's about 1 million zip ties involved and about 2K of duct tape, or 100-mile-an-hour tape as I like to call it. But back to the geeky stuff. So some platform requirements for this. I need a dedicated attacking and sniffing interfaces, and I'll talk about why a little bit later. Had to be easily adaptable to new software and techniques being introduced. A simple, non-intrusive readout for the rider would also be a bonus. I mean, you don't really have access to a keyboard while pedaling down the motorway, so. And the ability to, if necessary, use the same gear in a car. So essentially, it needs to be a protective, detective electric eye. The hardware and software that's been used in this build, we've got a Raspberry Pi, we'll call it Wi-Fi. So this powerful heads-up display for the rider is a couple of microchip router boards, which are made by a bunch of crazy Latvians, for microboards left and right. These are our sniffing and attacking devices, and Sony Bio Network is being used as the brains of the operation for the Wi-Fi. When you put this into Visio, it looks something like this. So it's all one flat layer 2 network. We've got the whiteboards left and right and their associated USB Wi-Fi interfaces. We've got the Wi-Fi network and USB GPS and the Wi-Fi for that, and also the Raspberry Pi and the heads-up display. So this is all attached over Ethernet. I'll talk about the software for a little bit. So there's 2 main suites of tools that I'm using for this. It's Kismet and Aircraft. Kismet is what we're using for going and gathering information. Basically, we have a client that displays information coming from the server. The server collects packets from a number of sources, and the drone can run essentially as a remote source. Aircraft MG is a suite of various tools, and it allows for easy orchestration of various attacks, things like deauthentication, ARP attacks, tied together, it looks a little bit something like this. So we have the Raspberry Pi, which is running our Kismet client, talking to the network, running the server, and our drones run on each of the router boards left and right. So the drones basically go and use their onboard interfaces, their sniffing interfaces, and then dump that data down a TCP socket, which the server picks up. For the attacking side of things, there's a set of processing scripts that live on WiFi, and these go and talk to the router boards left and right. The pipeline, so the main purpose of this is to run the Kismet server. Initially, I thought it would be awesome if I could build everything off one Raspberry Pi, except running a Raspberry Pi with a single drone gave me about 2 meg of memory free afterwards, so that wasn't really a good idea. Instead, opted for the network approach. So the Kismet server runs on this device. USB-attached GPS is used for gathering the locations of the networks that are mapped. The onboard wireless is used as an access point so that one can actually go and administer the infrastructure wherever. So basically park up at pub with laptop and go and deal with stuff. This was really easy. We just hosted a BDMD HTTP3 server. I think there was about 10 lines of config in each, so it's really, really simple. Dedicated attack interface is also added to the pipeline via USB. So this is put in for running rogue access points and doing slightly more convoluted and involved attacks that you can't really automate on each of the router boards. And of course, it runs the Python scripts to go and orchestrate said automated attacks. Our router runs left and right. So as I mentioned, these are microchip devices installed with OpenWRT, which was a real mission in of itself. Not because running OpenWRT is particularly difficult, simply because none of the documentation that's available on the internet tells you that after you TFTP boot the bastard, you have to take the cable out of port 1 and put it into port 2 before it will start applying the pings. So yeah, that was a wasted evening. I was not happy. So the Kismet drone was running on these devices that feeds the server running on Wi-Fi. Dedicated attack interfaces each via USB as well. So these devices have a single USB port available, and thankfully OpenWRT makes it really easy to add support in for Atheros-based USB Wi-Fi interfaces. The reason I have 2 devices, well, actually it's really simple if you haven't figured it out already. Basically, I wanted to capture both sides of the road at once while going in and riding along. The 90 per device was not really that dear, and the bonus of having USB attached attack interfaces is that if instead of having to run a really long antenna or something like that and deal with attenuation and bits and pieces like that, instead the interfaces can be placed basically anywhere on the bike through the use of a USB extension cable. Easy. The idea behind actually having dedicated sniffing and attack interfaces is a lot of the examples that you see on the net around doing deauthentication attacks and things like that basically involve using the aircraft suite and aerodome and actually locking aerodome down into a specific channel. I can't really do that because I don't have access to a keyboard, and going and running around all these different things on a specific channel just seems like a stupid idea. So how this works is the dedicated sniffing interface just doesn't get touched. So it'll pick up whatever it sees, and the scripts can go and set the additional interface onto whatever channel it needs to be set on, and then go and orchestrate whatever crazy attack it needs to. So the Wi-Fi, this bit was a little bit it's a Raspberry Pi, and it's actually powered off the network. Yeah, for USB power sources. It's a real simple architecture build. I think it took about 40 minutes to get it running. This one's the Kismet client with a tweaked layout and some gutted video glasses attached via RCA output for the heads-up display. I know really it's just a screen that lives in the helmet, but still. I tried to go and get a photo a little bit closer. You can sort of see Kismet running in that photo to the right. I tried to go and get a camera in there to get a really decent photo of what the output looks like, but sadly the macro setting was not happy with the focusing lenses and things like that. So instead, I just grabbed a snapshot out of the phone. So this is kind of what it looks like. This is what I see in color. We've got some basic data on the right-hand side, so the amount of time it's been elapsed, the networks that have been seen, packets, etc., etc., etc. A list of access points. These update with the latest access point seen coming up to the top. The GPS information is coming in, and it's really, really distracting because it actually gives you an accurate speed layout, speed readout, sorry, and some info logging. So the great thing about the info logging is that all those logs have nothing to do with the client at all. They're all coming from the Kismet server. So if one of my router boards decides to explode, I'll get a big highlighted error message that says, hey, you should probably pull over and go and fix your shit. The most useful part of this, though, when everything is running correctly, is that the packet graph, the packet and data graph, gives you a really good indication of when you're going through an area or a highly populated area that has a lot of access points. The reason this is useful is it kind of gives you an indication that, hey, there's a lot of stuff around here, so maybe circling the block a couple more times is a good idea. The mounting within the helmet is real simple, so it's just basically stuck to the top of the helmet, which means that if you're looking through the helmet, the screens end up just about here, above one's eyebrows. A problem that I faced with this build specifically was that I got everything mounted and everything was working. I was looking up at the screens and everything was really blurry and just terrible. So I went through trying to check the Raspberry Pi, check RCA cables, all that sort of stuff to figure out what was happening. Turns out, if you wear glasses, you're screwed. You have to put contacts in. Now, powering it all. This is where it all got a little bit. It was kind of complicated, but then it got really, really simple. A standard ward driving setup usually revolves around using the cigarette lighter in your car. And using that to go on power an inverter and attaching all your various power supplies and laptops and stuff like that to said inverter. It seemed like a little bit of a convoluted setup to me because it was basically taking DC power, converting it to AC, and then back to DC. So, screw it. I figured that I've got a DC to DC converter with a custom harness to go and actually power the devices would be a way easier way of going about it. There was a small problem with this though. And the problem here was that a DC to DC converter would take the input voltage range of, say, from 11 volts to 15 or 16 volts that the bike will experience while not being off, being off or while charging. That would have set you back about $190. And $190 is a low bike item, so I really wasn't happy to party with that much money. Thankfully, trading came to the rescue. So this DC to DC converter was $9, which I was quite happy about. What this does, or what it's designed to do rather, is on one end you have your cigarette lighter plug, and on the device there's a set of switches that you can use to go and select what voltage you want to come out, and at the other end you plug in whatever adapter you need for your specific laptop, and hey presto, you've got laptop power for your car. This runs basically exactly like any other DC to DC converter. It goes and takes a wide input range of voltages and spits out whatever you set it to. And the 80-watt total power was more than enough to actually go and make everything work. So I was quite happy about that. Put it all together and set up on my coffee table. It actually ran quite well. I'm not sure if you can see that multimeter readout, but that was basically 12.5 volts coming off the battery that I ripped out of an XS650, going and powering the devices, so the laptop, the Raspberry Pi, and the associated devices. You don't need crappy or wooden coffee to actually go and make this work. So mounting. Mounting this was actually really simple. So basically what I've got here is just two Oxford saddlebags, which I stole off my brother. I love that guy. So yeah, it's just two Oxford saddlebags. So basic brackets that you put inside to make sure it keeps shape and doesn't flap around and move too much. One side we have a router board. So that's the right side, and on this side we have the network, the router board, Raspberry Pi, and all the associated electronics. I could have gone and hidden the wiring that's running through this a little bit better, but I don't know, I'm kind of a fan of cyberpunk, right? So I figured I need to. All the wiring is actually running to bullet cages, so what this means is that the flywheels that go to the battery can be disconnected and wired back into a normal cigarette lighter plug, so you can use the thing in a cage. Apparently it's unreasonable of me to expect all my co-workers to ride motorcycles. So this actually ended up working out. This is my test lab. So here, basically, you can see the bike in the background. I'll just go on and use the SSH to connect to each of the router devices to go and check some things that are running. So you might as well have a poke around. I'm pretty sure I remember to turn this on. Come on, buddy. Sweet. You want to see that? Okay.
Make it bigger, baby.
You're bigger. Hey, does anybody know how to drive terminal on Apple?
Still Linux.
Not really. BSD called, they want the kernel back. Right. So here, let's just ahead and connect into Wi-Fi. Great. So here we go. So we're basically connected into the network that's going to be running as our access point on the Kismet server. So here you can see a whole bunch of Kismet data that's going to bring up my hard disk. This is just a basic backtrack build. The reason for using backtrack was I didn't really want to go and spend too much time trying to get dependencies and libraries and various bits and pieces running on a custom build. And this way, if I want to pull over and go and run Metasploit for whatever reason, then that's totally possible. So the router will actually go and fire up Kismet by default. So it just works a simple init script called the Kismet drone. So you flip the switch and they just work. So I'll go ahead and start the Kismet server. Great. So that's all running and happy days. Maybe not. Okay, maybe I did not remove the shit on. Oops, my bad. Right, so the router looks take a little time to power up, but thankfully this is all wired with a single kill switch, so you flip the switch and hopefully it works. Oh, difficulty, you suck. Sucks so bad. Excuse me. Okay, I bet at the risk of how long it takes to open WLT to boot. Great. Okay, that's what everybody had happy thoughts. Lots and lots of happy thoughts. Alright, so we're kind of running out of time, so I'll go and hurry this up a little. So that's all happy days. Let's go and take a look at one of the routers. Right. So this is our router build. We have two of these. It's really basic North WRT build. These devices aren't really that massive in spec. Like they've got 32 meg of RAM. Atheros processor. So they're pretty basic devices, but they seem to fit the purpose quite well. I can't really show you a readout of what I see in the heads-up display, but instead, I can just go and connect to the Raspberry Pi and show you what the outputs are. Sweet, so once we connect here, we just run Kismet client. It likes to think about this. Yeah, the client takes a little bit to fire up and actually start getting data from the server, provided I didn't accidentally control the server. Establish connection, see. So the establish connection to the Kismet server, and we should be seeing data coming through the server. Sadly, I don't think we're going to be having any GPS data because it takes a little bit to get a lock after doing the reboot. But anyway, let's go. That's what the layout kind of looks like. Yeah, so the network is pretty basic. If you understand how UX works, that's pretty easy to get your head around. Mapping is where the sort of fun stuff starts to happen. So the GPS unit is attached to the brains of the operation. This costs like $45 and works with backtrack out the box. Pretty sweet. Just ran GPSD, clip the thing in, and it worked. And with the joys of Kismet, one can go and connect to the motorcycle, pull the map access points across, and then use GIS Kismet to spit out overlays for Google Maps and things like that. GIS Kismet passes XML data from Kismet and turns it into an SQLite database. So if you only want to map open access points, or if you only want to map access points that have a specific instance ID, then that's all really possible. When you do this, it ends up looking something like this. So here's a little extract that I took from my test lab. Here. So there we're going to Kiwicon.k now. Sadly, I don't really have too many access points to show you, but I think it should be enough. So this is roughly 10,000 access points across the country. Please ignore the blank spot in white room. I don't know anything about that. So here we go. We're going and looking at some stuff in Portland. Basically, what happens is you see, you get all the pretty Google Earth animations of going and splitting stuff and all that sort of jazz. What happens here is that when you go and find some access points of various names and things and bits and pieces, you can click on any of these access points, and what it will do is actually show you any clients that seem unique to it. The great thing with Kismet as well is if you have hidden SSIDs, if Kismet can gather enough data, it'll just show you the real SSID name, which is a real bonus. So moving back on, while I'm going and scrolling through Google Earth, the various colors that you see going around, different colors represent different states of encryption for each access point. So red is no access, orange is WEP, light green is WPA, and dark green is WPA2. So here we have Wellington. It's much the same data that was seen in Wellington, in Auckland, sorry. Various, like, Parliament trusted. It's an interesting one. So you have all sorts of things going and floating around. And the great thing about this is really all I had to do was just go and write around. I did have one thing that was quite interesting. So we decided to stop off in Oakland the way down from Auckland, and I found an access point that really just made this whole project, man. It was great. So while sitting in St. Cosmo in Oakland, I decided to go and connect into the bike and see if I found anything interesting, any sort of crazy access points or anything like that. And funnily enough, we did. I didn't see any clients getting that at the time, but the dude really does get points for ingenuity. So yeah, that's going to be my favorite thing about this entire trip. Okay, so thinking about how you can actually go and use this data. Well, I don't know. So some may think that right around mapping access points, you just get a whole bunch of data, where you see various bits and pieces. But if you see an access point like this, for example, which is what I assume to be the default config of DDWRT, it's an open access point with a load of clients. What could we possibly do with this? Well, Ethercat called, and he wants to know why you don't come around anymore. All right, so moving on. Obviously, just monitoring things is causing nobody real enough chaos. So, how do we capture handshakes while riding? Basically, when trying to go and crack down the PA networks, one needs to go and capture the handshake before they can actually have anything to crack. So, auto-deal is the answer for this one. The autotron.py goes and connects to the Kismet server instance and spits out APAC commands to be run on each route port. The great thing about Kismet is that all the communications that are happening between the client and the server and the drones is all in clear text. So even though the documentation didn't really give me everything that I needed, it was pretty easy to figure out how things work. The initial idea was to have a release the Kraken button somewhere on the motorcycle. But the idea of having to pay attention to a heads-up display, hit a button, and go down the one way at whatever speed is just, it didn't seem like that good of an idea. Thankfully, the clear text communication protocol made automatically doing this quite easy. The deauthotron output looks something like this. So basically what happens is we get a deauthing AP, we go and capture the MAC address of the access point, the MAC address of the client, and the channel that it runs on. and we go and pilot some commands and send it through to each of the router roles. The router roles are defined in the config file, and it can be as many as you like. So, for example, if at some point I decided to go and lose whatever little dignity I had left and bought a Harley Road King, I could run like 8 of these, right? And probably on one new server, it would be great. Right, so where to from here? The foundation has been laid, but the one thing is being stranded really sucks, right? So a lossless power system is something that needs to be built. Thankfully, this is quite easy. A direct line from the lossless rectifier to a separate auxiliary battery would solve the problem immediately. So what that means is when the bike isn't running, your gear is just draining off the auxiliary battery. When the bike is running, the charging circuit is going and powering both the battery dedicated for the motorcycle and the one that's dedicated for the gear. So you drain the battery out of power, worst case scenario, oh no, you have no more Wi-Fi gear. Auto experience is the other one. Sadly, I didn't have enough time to actually go and implement any of these, but going and mapping out how many auto access points one can find around New Zealand, hence there's a lot of Linksys ones. It would be quite easy to go and get the attack interface on the network to go and connect to an open access point that it finds with the correct SSID and MAC. Fingerprint it to make sure it's right, reconfigure it to do whatever it needs to, and then profit. Maybe perhaps some automation reader attacks. The sky is really the limit. So to summarize this, with a few simple things, namely a chunk change, a soldering iron, an understanding that power is currently multiplied by voltage, and some basic Unix skills, almost anybody can go and create their very own Wi-Fi-attack-cycle and terrorize their neighbors too. They think they have private lives, but nothing of the kind.
Well,